Let's try and understand entropy now. Entropy is represented by symbol S, and delta S is difference in entropies. Alright, and entropy means disorder, randomness. Alright, now let's understand it via example. The ice heated gets converted to water. Heated gets converted to steam. Where do you feel entropy is maximum? Obviously, maximum entropy would be in steam. The molecules would be too very disturbed. Whereas in case of water, it would be disturbed much lesser than in steam. Whereas in ice again, there's hardly any disturbance. So obviously entropy is maximum here, slightly less here, and least here. Alright. Now, as per theory of entropy, whenever delta S, that is change in entropy, I call this as S1, S2, S3. So S3 minus S2 has to be positive for reaction to be spontaneous. Yes, we find that steam S3 is greater than S2, so S3 minus S2 would be positive. Similarly, it goes here also. S2 minus S1 would be again positive because disorder over here would be much more than that in ice. So yes, understood. This blue arrow is certified correct. So it has to be like that. So S3 greater than S2 greater than S1, therefore del S is positive, so forward is favored. Understood. Now, before going ahead, I would like to also bring to your notice formula for del S. This is Q reversible divided by T, where Q reversible is heat transferred to system in reversible manner. That is, it goes there. Now, for example, here I put in heat here. It gets converted into water. If I take out that heat, it should get convertible. It should get converted to ice again. So that's what I meant by reversible. All right. And temperature at which transfer occurs in Kelvin. Temperature would be T in Kelvin, and temperature at which transfer occurs. That's what it is. So these all part understood, formula understood, and for spontaneity, del S has to be greater than 0, or we can say del S has to be positive, explained. But the situation is, as per this, if we go reverse, it shouldn't be feasible. Don't we condense steam to water and water freeze to ice? This process is also feasible, one which I have drawn in red arrows, one which I have drawn in red arrows is also feasible. Then why? Then what? Here del S would be negative because entropy over here would be much lesser than entropy over here. So if I do S2 minus S3, it would be negative because here S2 is lesser than S3. Same thing goes here also. So what? So let's understand. So what happens? So the theory doesn't click. The system we saw forward feasible, but backward not feasible, yet practically feasible. As per del S theory, not feasible backward. Ice to steam, feasible in forward direction as per delta S theory, as per entropy theory, del S has to be positive. But as per del S theory, entropy theory, reverse process, that is steam to ice, not feasible because del S is less than 0. So what? So to save the theory, dropped in second law of thermodynamics. What is it? Total entropy of a system and its surroundings increases in spontaneous process. So we have got to prove that it has to be plus. It has to be plus. So how is it plus? Del S total. We also introduce surrounding into it. So we say now our statement goes as delta entropy of system plus delta entropy of surrounding has to be greater than 0. Alright, and this is what it has to follow. When del S total is greater than 0, process is spontaneous. When del S total is less than 0, process is non-spontaneous. And when del S total is equal to 0, then the process is in equilibrium. So surrounding comes into picture. But we are more interested in system, del S system, than surrounding. So a new thermodynamic property called Gibbs energy introduced. And what was it? G is equal to H minus Ts. We know G is Gibbs energy, H is enthalpy, which we have studied a lot now, T is temperature in Kelvin, and S is entropy. So change in Gibbs energy would be equal to del H minus T del S. Alright, so now new rule set in. So, and if del G greater than 0, process is non-spontaneous, del G less than 0, process is spontaneous, and del G is equal to 0, process is in equilibrium. So if you can just compare these two. You can compare this with this and see. Just to keep in mind, what I say is that negative has got G in it. So keep it in mind that when del G is negative, the process is spontaneous. Just a way to keep it in mind, negative G. So G spontaneous when it is negative, that is less than 0. So the counter is true for entropy. Counter is true for entropy. Alright, so just a way to keep it in mind. Alright, so that's what I talked about. Introduction of Gibbs into thermodynamics. Alright, so now let's understand Gibbs a little bit in detail. Alright, now let's understand Gibbs energy bit in detail. Suppose the reaction is occurring this way. A moles of A plus B moles of B giving C moles of C plus D moles of D. Alright, this is the reaction which is occurring. And this is the reaction quotient. This is the reaction quotient and this is the time. Okay, let's understand this way. Now this is the reaction which is occurring. Alright, so as per reaction quotient, reaction is moving forward, and then it comes to an equilibrium. At this point, when it touches the equilibrium, we say QC, reaction quotient, is equal to equilibrium constant. Alright, but when it is below equilibrium constant, we understand that QC is less than KC. Now in case of equilibrium, now suppose the reaction is at equilibrium at 70%. So at certain moment of time, it also crosses 70% and again gets back into, say it crosses to say 70.5% and then it again gets back to 70%. So when such is the state, at that time QC, reaction quotient, is greater than equilibrium constant. Alright, so that's the relation. So you have QC greater than KC here, you have QC equal to KC at equilibrium and QC less than KC till it reaches equilibrium. Alright, so reaction quotient versus time. Alright, so now let us get into a bit of derivation aspect. Del G is equal to del G standard plus RT, R gas constant, T temperature, ln log to the base E, ln QC. Alright, QC already I mentioned is reaction quotient. So this can be modified, QC can be modified. A formula for equilibrium constant, product of concentration of products with their moles at the top divided by product of reactant with their moles being their power. Alright, so we know this was it. This was now we are talking in this term, right? In this term, till this much. So del G, we have got to find G at varieties of places. Here I will find G, and then here we'll find G, and we will find the difference. We get del G. Alright. Now del G 0 plus this, just substitute the formula. Then we can also substitute it in terms of QP. It's just like we are done with KC and KP. Now we knew that KP is equal to KC RT raised to del N. When we talk in terms of QP, we talk in terms of pressure, then all this gets converted into pressure format, partial pressure format. Alright, so this got converted. Now we are talking in terms of gas here, so it is in terms of pressure. Then again pressure, what is the relationship between pressure, QP and QC? The relation is RT del N, which I would derive in my other video when I do equilibrium constant. So QC RT raised to del N, we know this formula, right? That's the relation. Now we know in terms of KC and KP. KC is equal to, which we have done in 11. KP is equal to KC RT del N. So same way, QP is equal to QC RT del N. So this is a relationship between these two. Alright. But at equilibrium, del G is equal to 0 and QC also is equal to KC, that we have already seen over here, right? So del G, this becomes 0, del G becomes 0, 0 is equal to del G standard plus RT ln KC, or del G standard plus RT ln KP. Now if I take RT ln KP that side, it becomes del G0 is equal to minus RT ln KP or KC. Alright. Now we all know that whenever we convert log to the base e to log to the base 10, we multiply it with 2.303. Why do we convert it to log to the base 10? So that we can use our log book. Alright. So 2.303 RT log to the base 10 KC, or it can also be minus 2.303 RT log KP to the base 10. Alright guys, I have tried my level best again with this thermodynamic chapter for making it as simple as possible. So please understand the video well and apply it for your numericals. Alright, I am sure it's going to help you out a lot. And I am doing my level best and would be doing my level best for presenting lots more videos on these topics for competitive exams. Alright, see them, absorb them well, and apply it for your competitive exams. Okay, and I wish you all the best. See you again.